We had studied temperature rise time relation of machine under heating as well as in the cooling conditions. So now we have to deal with the problems relating to it. Before going to the problem, we need to know each and every term and also its units. So moving on to the first problem, it's a basic problem and it's very simple. The first problem is like this. The field coil has a heat dissipating surface of 0.15 meter square and a length of mean turn of 1 meter. It dissipates loss of 150 watt, the emissivity being 34 watts per meter square degree Celsius. Estimate the final steady temperature rise of the coil and its time constant if cross section of the coil is 100 into 50 millimeter square. Specific heat of copper is 390 joules per kilogram degree Celsius. Space factor is 0.56. Copper weight is 8900 kilogram per meter cube. So from the question it is we have to find final steady temperature rise of the coil and also its time constant. So final steady temperature rise of the coil is denoted as theta m and its temperature constant is denoted as Th. Okay, so the equation for theta m is q by lambda s. So we need to know what is q. So q is the power loss or heat developed in watts or joules per second. So in the question it is given as 150 watts. So q is 150 watts. Now is lambda. Lambda is a specific heat dissipation and its unit is watt per meter square degree Celsius. But in question it is given as emissivity, that is 34 watts per meter square degree Celsius. So we need to know each term's unit. So it will be easy to find the term. So lambda is given as 34 watts per meter square degree Celsius and S is the cooling surface area. Okay, that is in meter square. So S in question is given as 0.15 meter square. It is cooling surface area as well as the heat dissipating surface area. So it is 0.15 meter square. So now we can find theta m. Final steady temperature rise is theta m is equal to q by lambda s. When we substitute all these value, we got theta m as 29.41 degrees Celsius. Now we need to find the time constant. The equation for time constant is Th is equal to Gh by S into lambda. So now we know what is S and lambda. So G, capital G. G is the weight of the active part of machine, that is in kilogram. So in question we need to know the weight. So from the question is weight is given as 8900 kilogram per meter cube, but that is the specific gravity. So we need to find the weight of copper, that is G. That is G is equal to specific gravity into volume of copper. Okay, so volume of copper in question is not given, but we know the length, area and space factor. So we can find the volume of copper easily. So volume of copper is equal to length into area into space factor. Since space factor is given, we have to take the space factor also. Okay. So length is given as 1 meter. Area is the cross section area of the copper, that is 100 into 50 in millimeter square, so into 10 raised to minus 6 into space factor, which is given as 0.56. So volume of the copper we got as 2.8 into 10 raised to minus 3 meter cube. Now we can substitute this to find the weight of copper. So G is equal to specific gravity into volume of copper. Specific gravity is given as 8900 kilogram per meter cube in the question. So when we substitute it, we got as 24.92 kilogram. So now we got the weight of the copper, G, and H. H is given in the question as 390 joules per kilogram degree Celsius. So H is the specific heat and it is given in the question as 390 joules per kilogram degree Celsius. When we substitute all these values or all these terms, we will get the time constant TH as 1905.64 seconds. So this is a basic and simple question to find the final steady temperature rise of the coil as well as the heating time constant. Next problem is the temperature rise of a transformer is 25 degrees Celsius after 1 hour and 37.5 degrees Celsius after 2 hours of starting from cold conditions. Calculate its final steady temperature rise and the heating time constant. If its temperature falls from the final steady value into 40 degrees Celsius in 1.5 hour when disconnected, calculate its cooling time constant. So the ambient temperature is given as 30 degrees Celsius. So in this question, we need to find the final steady temperature rise and heating time constant, as well as we need to find the cooling time constant. So before also we know the machine under heating condition as well as cooling conditions, final equations. So let's move on to the answers. So first we need to find the final steady temperature rise and the heating time constant. So in the question it is given as when T is equal to 1 hour, theta is equal to 25 degrees Celsius. And second condition is when T is equal to 2 hour, theta is equal to 37.5 degrees Celsius. So two conditions are given. So we need to find theta m, that is final steady temperature rise, and heating time constant Th. We have only two conditions, that is 1 hour we get theta equal to 25 degrees Celsius, and in 2 hours we get 37.5 degrees Celsius. So we know the basic equations as theta is equal to theta m into 1 minus e raised to minus t by th. So we need to put these two conditions in order to solve the terms theta m and th. So the first equation is 25 degrees Celsius, that is theta in 1 hour. That is 25 equal to theta m into 1 minus e raised to minus 1 by th. That is equation 1. And second condition 37.5 degrees Celsius in 2 hours. That is 37.5 is equal to theta m into 1 minus e raised to minus 2 by th. Okay. So on solving equation 1 and equation 2, that is dividing equation 2 by 1, we get 37.5 by 25 is equal to 1 minus e raised to minus 2 by th by 1 minus e raised to minus 1 by th. Okay. So e raised to minus 2 by th we can represent as e raised to minus 1 by th the whole square. Okay, exponential terms equation. So it is same like e raised to minus 2 by th. So now e raised to 1 minus e raised to minus 1 by th the whole square can be represented as a minus b into a plus b4. Okay. So 1 minus e raised to minus 1 by th into 1 plus e raised to minus 1 by th. The denominator and numerator term gets cancelled. Now 37.5 by 25 is equal to 1 plus e raised to minus 1 by th. So from here we got e raised to minus 1 by th is equal to 0.5. That means minus 1 by th is equal to ln of 0.5. That we got as minus 0.6931. Okay. Now th we got as 1.4427 hour. Now we have to substitute th in any of the equation 1 or equation 2. Then we will get the value of theta m. So we got theta m as 50 degrees Celsius. So first question we found theta m and th value. Now moving on to the second question that we need to find the cooling time constant. So condition is given as if temperature falls from the final steady value, that is the value which we got right now, that is theta m, we got as what, 50 degrees Celsius. So from that value it fall into 40 degrees Celsius in 1.5 hour. So when it disconnected, we need to find the cooling time constant. So we know the cooling condition equation as theta is equal to theta I into e raised to minus t by Tc, where Tc is the cooling time constant. Okay, and theta I we know as the what, initial conditions. No, initial temperature rise over ambient medium, that is the theta I in cooling condition. Okay, so theta I is now theta I is the theta m which we got from the previous value, that is theta I is equal to 50 degrees Celsius, and theta it is given as a temperature falls from the final steady value into 40 degrees Celsius, that is from 50 degrees Celsius to 40 degrees Celsius, that is 50 degree minus 40 degrees Celsius equal to 10 degrees Celsius. So here we need to find theta first, that is it is given as the temperature falls from the final steady value into 40 degrees Celsius. So that is theta, and also theta I is the theta m from the previous question. So now we have to substitute theta is equal to theta I into e raised to minus t by Tc. So theta we got as 10 and theta is 50 and t is 1.5. Now we will get Tc, we got Tc values 0.932 hour. So it's a simple question in which we applied both the heating condition as well as the cooling condition. So we need to know that here the final steady in cooling condition, it is given as final steady value into 40 degrees Celsius, that is theta is given as 50 minus 40 degrees Celsius, and theta I, the initial conditions of this cooling condition, is obtained from the previous value, that is theta m. So this is a simple question here in which we apply both heating as well as the cooling condition. Next question is, a 400 kVA transformer has its maximum efficiency at 80% of full load. During a short full load heat run temperature rise after 1 hour and 2 hours is observed to be 24 degrees Celsius and 34 degrees Celsius respectively. Find the thermal time constant and final steady temperature rise of the transformer. If by use of a fan the cooling is improved so that the rate of heat dissipation per unit area per degree rise in temperature is increased by 15 degrees Celsius. Find the new kVA rating possible. First one, for the same final temperature rise as before. Second one, if the allowable temperature rise taken as 50 degrees Celsius. So in this question additionally we need to find the new kVA rating also. So rest is like the same we found in the heating time constant and heating equations. So in addition to it we need to find the new kVA rating also. For that they have given the maximum efficiency of the transformer at 80% full load condition also. Okay, so from the question, first we need to find the thermal time constant and final steady temperature rise of the transformer, that is Th and theta, which is so easy to find. For that they have given two conditions like T is equal to 1 hour for theta equal to 24 degrees Celsius and T is equal to 2 hour for theta is equal to 34 degrees Celsius, and we know the heating condition equation as theta is equal to theta m into 1 minus e raised to minus t by th. So substitute these two conditions, we will get two equations. On solving equation 2 divided by equation 1, we will get term TH, and this TH is substituted in theta, the first or second equation. Then we will get the value of theta m. So now we got TH and theta m. So TH is the thermal time constant, and theta m is the final steady temperature rise. Now we need to find the new KVA rating. So to find the new KVA rating, there is two possible conditions also they have given. First one is to find a new KVA rating for the same final temperature rise as before. And also second, they are telling us to find if the allowable temperature rise is taken as 50 degrees Celsius. So in order to find the new KVA rating, they have given the transformer maximum efficiency condition at 80% of full load. So first we need to know the maximum efficiency condition of a transformer. Okay. So at maximum efficiency, we have studied in our previous semesters. Like for maximum efficiency, copper loss is always same as core loss. Okay. So copper loss is X square Pc and core loss is Pi. So here the X we can take as 0.8 since in question is given as maximum efficiency occurs at 80% of full load. So X we have taken as 0.8. So at maximum efficiency, copper loss is equal to core loss, that is X square Pc is equal to Pi. That is 0.8 square Pc is equal to Pi. So Pc we got as 1.5625 Pi. Therefore, total loss for full load is copper loss plus core loss. So we got as 2.563 Pi. So we will check the first condition. So here if a fan is used, if a fan is used, the first final steady temperature rise theta m is obtained from the previous value and TH also we obtained. So if a fan is used, first we need to find the allowable losses. So allowable losses is in question it is given as please read the question. If by use of a fan the cooling is improved so that the rate of heat dissipation per unit area per degree rise in temperature is increased by 15 degrees Celsius. So it is increased by 15 degrees Celsius. So the new allowable losses are 1.15 times the allowable losses with this 400 kVA transformer or output. So allowable loss is equal to 1.15 into allowable losses of 400 kVA, that is 2.563 Pi. So allowable losses we got as 2.947 Pi. Now the allowable copper loss is total allowable loss minus Pi. So 1.947 Pi. Okay. And Pi we know as copper loss is equal to core loss. So Pi is equal to Pc by 1.563. So when we substitute this Pi value to allowable copper loss, it is it is obtained as 1.245 Pc. Okay, now it's easy to find the new output kVA. Suppose the new output is X times 400 kVA, then the copper loss, that is X square Pc, is equal to 1.245 Pc. Okay, so now we got X as 1.116. So the new output is X times 400 kVA, that is 1.116 into 400, we got as 446.4 kVA. Okay, so this is the first condition. Now the second is they have given as we need to find the new kV if the allowable temperature rise taken as 50 degrees Celsius. So the maximum allowable temperature rise with 400 kV output is 41.09 degrees Celsius. That is rise to, okay, that we got from the first condition. That is theta m is 41.09 degrees Celsius. That is rise to 50 degrees Celsius. So everything will be same. Surface area and everything will be same. So now to find we need to find new theta m, because they have clearly told that it is rise to 50 degrees Celsius. So new theta m is 50 by the previous value 41.2. Okay. So that therefore, I mean, now we found the new theta m value. Also we need to find the allowable losses. So that is previous it was 1.15 into 2.563 pi. Okay, so for the new question it is 1.15 times the allowable loss with 400 kVA. Okay, so 1.15 into 2.563 pi into what, new theta m, that is 50 by 41.2. Now we got the allowable loss as 3.575 pi. Now next we need to find the allowable copper loss, that is this 3.575 pi minus pi, and pi we know that copper loss is equal to core loss, so pi is equal to Pc by 1.563. Now we got allowable copper loss for the second condition as 1.644 Pc. So when it is x times 400 kVA, we need to find the x value, that is x square Pc is equal to 1.644 Pc, since it's maximum efficiency. So new output is this x value into 400. So second we got as 512.874 kVA. So these are some problems dealing with the temperature rise time equations in the heating as well as in the cooling conditions. So these problems are very much important for the exam also.